And I also have new bold markers now. So hopefully these work better.
That's always a perk.
So I'm going to call this, so this is lecture 4. Now let's call it maps. What are they good for? So I'm going to try to kind of sell you on maps. Because we're all used to differential equations, we're used to flows and things of that sort. But hopefully I can show you that maps are quite useful as well. So for the homework, I'll kind of assign you problems as we go through the lecture. Okay, so maps are sometimes a more natural way of modeling certain phenomena. And we'll see some of that. So usually if there's a recurrence, then it might be a good idea to model it using a map. And they can be easier to analyze sometimes, but not always. So sometimes they're more difficult to analyze, but sometimes they're easier to analyze. So some of you have seen Poincare maps, so that's why they use that, because sometimes it's easier to analyze the map. And they're much easier to simulate than ODEs. So why is that, though, do you think? So for ODEs, you need some really complicated numerical schemes like Runge-Kutta or things like that in order to solve it. And sometimes they don't even work, right? So if you have a very funny ODE, sometimes the nonlinearity is so great, the stiffness is so great that it's not going to really work to approximate the solution very well. Whereas with maps, and you'll do some of this, I want you to do some numerics on maps for homework. So you'll see that all you need is a for loop and then some arithmetic operations inside that for loop. So that's all you really need for maps. Whereas for ODEs, you need some more complicated schemes. So let's first define what a map is. And I kind of wrote this definition, so let's see if you all agree that this is the definition of a map. So maps are time discrete, so that's important. So you're used to ODEs where the time is kind of continuous. But here, we're thinking of discrete time. So we're not interested in the time exactly, but we're interested in what happens after a certain number of times, after a certain number of repetitions. Doesn't matter what the time frame is between those repetitions, basically. So maps are time discrete dynamical systems. Represented by so some of you may not have seen recurrence equations, but this is a recurrence equation. Hopefully I spell recurrence properly. Recurrence relation xm plus 1 equals f of xm, and xm can be in, say, Rn. So that's how I would define a map. So basically, you give me a starting value, and then for every single time period, it's going to just iterate that value. So for numerical schemes, when we use Runge-Kutta and stuff like that, basically what we're doing is taking the differential equation and changing it, we're discretizing time and changing it into a difference equation, kind of like this. So with numerical schemes, we kind of do this. But here, we'll go straight to that. So one of the great things about maps, though, is that it can give you a very simple equation for chaos. So we're not restricted with dimensions with maps. So we don't have to be in 3D to have chaos with maps. We can be in 1D and still have chaos. And we'll see that later in the class. So I should remind you of some properties for maps. So I know some of you have seen maps. So let's go over what a fixed point is. So what do we think of when we think of fixed points?
No change.
Okay, so if we're on that point, we're not going to get off it, right? We're going to stay there. So that's what a fixed point is. So what do we think a fixed point for a map should be, though? So for an ODE, it's when dx dt equals 0.
When xm plus 1 is equal to the function, is going to be equal to xm.
Okay, so when x star, let's say, equals f of x star. So if we have a map, xm plus 1 equals f of xm, then x star is going to equal f of x star. So that's the idea of a fixed point for maps, but why is it that? Why is it like that?
So if you're at the fixed point, then even doing whatever function on it won't change its value.
Okay, so as what happens?
As you go through like one of those cycles or
As you iterate.
One cycle, or, okay, as you iterate, so
times.
how many though? Infinitely, right? So let's do this. Let's take that, and let's take limit as m goes to infinity of x m plus 1, right? But then this is going to equal the limit as m goes to infinity of xm, right? So these two limits are equal because it's going to infinity. So then we could just call this x star. So since these two are equal, we can call it x star and then plug it in and then try to find out what x star is. So that's why we define a fixed point like this. So this basically means that if we're on the fixed point, we're not getting off it. So now let's do an example with this. So let's take the example, and now I'm going to use n to index it. xn plus 1 equals xn squared. So let's look at that example. So we have this recurrence relation, or a difference equation, or a map that's represented by this. So then we're just going to plug in x star for xn and xn plus 1. So we get that. But then that gives us that x star squared minus x star equals x star times x star minus 1 equals 0. So then we just solve for x star. So then we get that x star equals 0 and 1. So that's how we find fixed points of maps. So for those who haven't seen this, any questions about finding those fixed points? So it basically just means that if x star equals 0 in this case, we see that it's xn plus 1 will always be 0.
So basically, we assume that x of either like n plus 1 is also equal to x sub n.
Yes,
Then
exactly.
you plug in x star for that and then solve.
Right, yeah,
So, okay.
that's it, yeah. So that's going to happen for all n, right?
Yeah.
So that's why.
So it's C++ all over again.
Yeah, so a lot of these concepts are used in computer science. Because obviously computers don't quite understand differential equations. Like we can understand differential equations, but computers don't understand it. they understand just very simple operations. So how do you break a differential equation down into simple operations? Well, you can just discretize time, and then you have a difference equation. So that's why a lot of these concepts are very natural for computers. So this is how we find the fixed points. So now let's talk about stability. Let me just see, that's what I want to talk about. So yeah, okay, so we defined fixed points, now we're going to talk about stability. So what is stability though? What does it mean for a fixed point to be stable or unstable?
You start at the point and then you will converge to it.
Okay, so that's stable. And if you start away from it, you're going to move away from it, right? So let me just tell you, let me remind you what it is, and then we'll prove it. So if lambda is greater than 1, so all those eigenvectors are going to correspond to the stable direction.
I'm sorry for being late. I believe that if I have one more unexcused, maybe you still have to report me.
Well, yeah, I'm just going over maps today, and we'll go from there. So the modulus of lambda less than 1 are going to be the stable, the eigenvectors there are going to correspond to the stable direction. And then lambda greater than 1 is going to correspond to the unstable direction. And lambda equals 1 will correspond to center. So it's quite similar to flows. So for flows, if we have our negative eigenvalues, those are going to be stable, and then positive are going to be unstable, and then 0 is going to be center. So it has a nice correspondence or nice relation to flows. But now let's prove this for the 1D case. So proof, and we'll only think about it in 1D. So how do we think we're going to prove this in 1D? So let's consider this. Consider a map in 1D. What do we want to call it? Or how do we want to write that?
Xn plus 1 is equal to xn.
Well, f of xn, right?
Yeah.
So consider that. So that's just a map in 1D. X and R in R1, in R. So consider this, and now what do we want to do for stability? So we know what stability is, so how do we write that? So you said if we start near a point, so what does near mean? So we want to make a perturbation near our fixed point, right? So we consider this and consider x star. So we want x star to be the fixed point, but let's think of it like this. So let's consider a perturbation near the fixed point. So xn plus 1 equals x star plus, say, cn. So we're going to think of a small perturbation near the fixed point. But what do we want to see with this perturbation?
That it goes to x star as you iterate that.
Okay, so what happens with the perturbation then?
Which you go to 0.
Okay, so either the perturbation is going to go to 0, or it'll go to 0 in backwards time, right? So that's what we think of when we think of stability. Or maybe our approximations that we're going to use is not going to work. So we'll see about that. But basically our goal is to see if this goes to 0 or not. So we have this. Now what do we want to do with this? So we have a perturbation, but how are we going to see if this perturbation goes to 0 or not? Okay, so we plug it in, right?
Yeah.
So we're just going to take this and plug it in to our map, right? So notice that we have xn plus 1 here, and so this is going to be x star plus Cn equals, so let's see, how do we want to write this? Let me see how I wrote it. So I write it as, so I should have written it as this. So we're going to take this, plug it in here, and then we're also going to plug it in here, except we have xn here. So we're going to write it like this. So f of x star plus Cn minus 1. So I believe in the notes I had it as n plus 1 here and n here. But it's the same sort of idea. So if you see this in the PDF notes, you'll see n plus 1 here and n over here. So we want to do this, but now we have to deal with this f, right? So how do we know, or do we know how to deal with this f? Or how do we deal with the f from previous classes? So let's say we have this big complicated f. Yep.
Derivative?
Okay. So what sort of idea do we get from derivatives? Like y derivative?
Let's see, like if the derivative is equal to 0, it wouldn't be changing or something like that.
Okay, but so we take the derivative when we want to approximate certain things sometimes, right?
Slope.
So what do we use to approximate f sometimes? So instead of, so I know you're thinking of linearization,
Yeah.
but now let's go further.
Okay.
So what is that called? Taylor series, right? So this is going to be equal to what? So how do we, what is the Taylor series of that? So those of you who have seen, so everyone's seen Taylor series, but so what is the Taylor series of this?
Around x star.
Yeah.
F of x star
Okay.
plus f of x star. Well, the derivative of f of x
So
star.
prime of x star, right?
Times c
Uh-huh.
n minus 1.
Okay. And then for this part, let's just leave it as order of Cn minus 1 squared. So these are higher order terms. So it's basically the linearization idea that Lucas said, except we do want to show these higher order terms. We want to write them down, but we don't want to think about them, basically. So that's why we do Taylor series. But now we have, so this is, if it converges, then this is a perfect approximation. I mean, this is not an approximation, this is exact, right? But now, suppose these higher order terms are small enough where we can kind of ignore it. So suppose that we can approximate this as this. So suppose that this is a good approximation. So let's say we can ignore these higher order terms. These higher order terms we're assuming is small enough. And we'll see what it means to be small enough. But suppose we can make this approximation. Now what do we notice? So we want to take this and plug it back in here, right? So let's write that down and then let's see what we notice. So this is f of x star plus f prime of x star Cn minus 1. So is there something we notice that can simplify that? That can help our argument?
X star is a fixed.
So how about that? What is f of x star?
Is it x star?
So that's just x star, right? So since x star is a fixed point, f of x star equals x star. So this is going to equal x star plus f prime of x star Cn minus 1. So we get that. But now we see that we have x star on the right-hand side and x star on the left-hand side. So then, this tells us that Cn equals f prime of x star Cn minus 1. So now we have a difference equation for C. So we have a difference equation for that perturbation. Since we have a difference equation for that perturbation, we can see if that dies down or doesn't die down. So now let's write C1. So we're going to give it C naught. So we're going to give it C naught so we can write down what C1 is. So C1, and before we do that actually, so let me just call this lambda. So let lambda equal f prime of x star. That'll make it a lot easier for us. So then C1 is going to equal lambda C naught. So we give it C naught. So that's a constant basically. So since C naught is a constant, it's easier to deal with. So now we want to write Cn in terms of C naught. So then by induction, we can write this. By induction, we can write Cn equals lambda to the n C naught. So do we agree with this? So if we're okay with this, then we can see what happens to Cn for some constant C naught. So that C naught isn't changing. We give it that C naught. But for that C naught, let's see what happens to Cn as n goes to infinity, or negative infinity. So here, what happens as say n goes to infinity? What can we write? What is the conclusion we can make, basically?
That if lambda is greater than 1, it's going to diverge.
Okay, so we can start with lambda greater than 1. So if lambda, so let me write it down like this.
And the perturbation is over.
If lambda is greater than 1, then what happens?
Then Cn grows bigger and bigger.
Okay, so how do we say that in a dynamical systems point of view, though?
That the perturbation gets bigger.
Okay, but so that means it gets smaller in backwards time, right?
Yeah.
So when in dynamical systems, when we talk about things diverging, we want to talk about it in backwards time. So it's converging in backwards time. So that's how we want to think of these things in dynamical systems. So if lambda is greater than 1, then as n approaches negative infinity, Cn goes to 0. And we can say the same thing for lambda less than 1. And when I say lambda, I mean the modulus of lambda. So modulus of lambda less than 1, as n goes to infinity, Cn is going to go to 0. So diverging basically means that if we're going in backwards time, then in backwards time, the perturbation is going to die down. So that basically means that if we look at it in forward time, then obviously it's going to go away from that fixed point. So we have this, but now what happens if the modulus of lambda is 1? So if lambda is on the unit circle. So can we say, or what happens to that limit?
It would stay at the same point.
No, so-
Xn would equal, Cn would equal C0 as time go backwards.
Okay, but so we're thinking of kind of the modulus equaling 1. So we can't say if the perturbation dies down or it doesn't die down, basically. So if lambda equals 1, yeah, we can say something about this, but we have to remember that we have higher order terms. So if lambda equals 1, then that means that's going to equal 1, right? So that means these terms become important now. So we can't say anything about the linear stability of it. So we would have to look at the center manifold, basically. So then if lambda equals 1, then we can't say anything about Cn, so we can't say if the perturbation dies down or not. So then we get a center, the eigenvectors in for lambda equal 1 is going to correspond to the center subspace.
Well, it's going to be like a linear center, but as you
Right.
pointed out, the nonlinear terms then become crucial. So when lambda is equal to 1, it depends on what the nonlinear terms are.
Exactly.
It's possible that the fixed point could still be stable because of the nonlinear terms, but it could be unstable. So the linearity there doesn't tell the story. You have to look at the full map, basically.
So yeah, this is only for linear stability, but if we need to look at the center manifold, then we can analyze the stability even further. So that's linear stability of the fixed points. So I believe I do an example for that too. So let's see what sort of example I do. So now let's consider the logistic map. So let's consider all these ideas for the logistic map. So this is what the logistic map looks like. So this is xn plus 1 equals r xn times 1 minus xn. So it looks a lot like the logistic differential equation, except it has different meanings for, say, xn equals 1. So here we see that if xn equals 1, then the population goes to 0 in the next cycle, basically, in the next time. So that basically means that when we're talking about xn equals 1, we mean just absolute capacity, where if we have some plants in a garden, then the plants have, like, there's so many that it basically makes the soil devoid of any sort of nutrition, so everything dies off. So that's a basic idea for that. But it's very similar to the logistic differential equation. So let's think of the fixed point of this. So when we did the example before, we had a fairly easy fixed point. But now we have a few more things involved. So let's try to find the fixed point of this, or fixed points. So how do we do that?
Do we substitute x star in for x sub n plus 1 and x sub n?
So we want to substitute in x star. And then we're going to do some algebra here. So this is what we're going to get. So we got x star equals r x star minus r x star squared. So that's going to be, we'll bring that to the other side, r x star squared plus 1 minus r x star equals 0. And then we're going to have So then we can factor out an x star. So x star times r x star plus 1 minus r equals 0. So we get that. So then we see that the fixed points are going to be 0, which makes sense because if the population is 0, then we're not going to get spontaneous growth. So x star is going to be 0 and r minus 1 over r. So these are the two fixed points. So now we want to find the stability of those fixed points. So how are we going to do that for this one-dimensional case? So we're going to develop the theory for the one-dimensional case because it's a lot easier to handle. And then we'll see what happens in higher dimensions. Yeah.
Take the derivative and see the
Okay.
rest of it.
So we're going to take the derivative of what?
Of the first function, rxn,
So let's-
1 minus xn.
Let's call it f of xn. So yeah, let's take derivative, but let's write it like this. So f prime of x star. So then that's going to be what? R minus 2r x star? So we get that? Yeah, that looks correct. So now, what do we want to do?
Plug in the fixed points.
Okay. So let's take x star equals 0. What do we get for that?
R is less than 1.
So we get
R.
f prime of 0 equals r, right? And then x star equals r minus 1 over r. So that's f prime of r minus 1 over r. So we're going to get, so then r and r cancel out. We're going to get minus 2r plus 2. So we're going to get 2 minus r. So we get that, right? Let me just make sure that's correct. So yes, it is 2 minus r. So we have those two fixed points. So I should mention this for the logistic map. We're thinking of xn between 0 and 1. And we're going to think of r between 0 and 4. So it doesn't really, it won't make too much sense if we think of the logistic map outside of these parameters. So that's what we're going to keep in mind. So I should write that down here. R is between 0 and 4. And I can even probably, well, okay, that wouldn't make much sense. But I can do that. And xn is between 0 and 1. So we're going to think about it in that domain.
Generally speaking, how do you
Mhm.
determine that?
What do you mean?
Just why is it 0 to 4?
Oh, okay. So basically, if we have r above 4, we're going to get some crazy results where the population basically spirals out of control.
Okay.
And it can't be negative because that's the carrying capacity.
Yeah.
So you can't like have, you know, it wouldn't make sense for it to be negative in this sort of model.
Okay.
So that's why. Of course, Professor Blackmore can give more insight to that.
Provide some insight?
Yeah, sure. I mean,
Well,
so
certainly if you look at the function is going to be negative if x is less than 0 or greater than 1. And you want to, that's why you want to confine your attention to the unit interval.
right.
Now the r less than 4, if this map is going to map the unit interval into itself, what you have to do is you have to look at the maximum value taken on by that function in the unit interval. Well, it's going to be at 1/2, and if r is equal to 4, the maximum is going to be exactly equal to 1. If it's greater than 4, and the maximum is bigger than 1, which means that if I have a population starting at that maximum, the next iteration will take you outside the interval.
Right.
So it's just a matter of setting up the mapping properly.
So yeah, Professor Blackmore has worked on a lot of ecological models, so he's quite an expert in this area.
Me and the logistic equation, perfect again.
So now let's try to figure out the stability of these fixed points though. So this is easy to get. So what is that going to be stable or unstable?
Depends on what R is.
That's true. It depends on what R is, yes. There is going to be some borderline cases such as, or one borderline case. So what's the borderline case? So what the borderline case for, or I shouldn't say borderline case, maybe say the center case.
When it's 1.
So when it's 1, right? So that's when, yeah, so the linear stability analysis isn't going to give us the information for that, but it's basically, so we'll see what to do when the linear stability analysis fails. But basically, if R is less than 1, then we're going to have that it's stable. And if R is greater than 1, we're going to have that it's unstable. And R equals 1, we're not too sure with this sort of analysis. And then how about for this?
3.
Okay, so for this, well, let's take a below 1 first. So what happens when R is less than 1? So it's unstable, right? So if R is less than 1, it's unstable. If now we can think about between 1 and 3. So what is it there?
Stable.
So it's going to be stable. And then how about if R is greater than 3?
Unstable.
So it's going to be unstable again, right? So we have these cases. But do we see any sort of anything that isn't quite satisfactory? Minus the fact that we don't know what happens at R equals 1 and R equals 3. What else is unsatisfactory with this? So if it's stable, right? If it's stable, then it's just stable. It goes into the fixed point and that's it. How about when it's unstable? So when it's unstable, it means that if we have, say, we're in a ball around that fixed point, and we go in backwards time, it's going to go back into the fixed point, right? But then what happens in forward time? Do we know what happens in forward time for the unstable case? Other than the fact that it's going to escape this ball. So we don't know, right? So that's kind of unsatisfactory for us, right? So for the unstable cases, I mean, it doesn't necessarily mean that it's going to blow up. It just means that if we try to confine it in a ball around the fixed point, it's not going to stay within that ball, right? In backwards time, it will. But in forward time, it's going to get out of the ball, right? So that's basically what it means to be unstable. So we don't know how it's unstable, basically. So we need to figure out a way to rectify this. And we want to kind of get a simple solution for this. So we're going to use this. We're going to use something called a cobweb plot. So let me see how I want to write this. So let me use blue and red. So let's make the first plot here. So these are going to be very useful for us. So here it's 0, here it's 1. So this is xn, and this is xn plus 1. Over here, so this is 0, 0, and this is going to be 1. So we want to be confined in this region, in this square. And now let's draw a line y equals x. So xn plus 1 equals xn. So what does that line correspond to? So xn plus 1 equals xn. Why do we want to draw that line?
Because we set the first equation equal to x.
Okay, so what does that give us?
That gives 6 points.
Okay, so that line is going to correspond to the fixed point. So anywhere where our function f of xn intersects this line, we're going to get a fixed point. So that's why we want to draw this line, so we can see where our fixed points are. Now let's draw the function, but first let's stay in the region below r equals 1. So let's write it like this. So here it's going to be r equals 1/2, and then say over here, sorry, not 1/2, r equals 2. And over here, say r equals 1. So we want to be below this. So let's draw it like this. So let's say that our f of xn looks something like that. So then we see that we only get this fixed point, right? So, well, I didn't do something correct here, I think.
Is this was intersection line twice?
Okay, so we have a problem over here, right? But let's see why. So if this is, so yeah, that's only going to intersect it once.
Okay, so
Right, okay. Yeah, got it if you
the
want to.
point x star is 1 minus 1 over r. If r is less than 1, it's not in the unit interval. It's negative.
Right.
So the only fixed point of interest will be the origin.
So yeah, although we do have a fixed point, we're not going to have a fixed point in this unit interval for that. That's why. So this is going to be our f of xn. So let me draw this in red. So this is how we want to draw a cobweb plot. So let's say we start at some point, right? So let's say we start over here. We're going to call that x naught. Then we want to see what happens to that x naught. So if this is x naught, then this is going to be x1. So that means that x1 is over here, but that becomes our new xn, right? So we're going to go from here, we're going to go to our new xn, but then we see for that new xn, so this is this is going to be our x1, but now our f of x1, so here it's f of x naught, right? So that's x1. But then when our x1 becomes our xn instead of our xn plus 1, we're over here. So our f of x1 is going to be x2, which is over here. So that's our x2. And then we do the same sort of thing. So this is going to give us x3, x4, and we can see that it's converging to that fixed point. So this is x naught. So this is actually, so let me write it like this. X naught, x1. And this is x1, x2, x2, x3. So those are the points that we're going to get. So this shows us what happens when r is less than 1. So we'll get a better idea when we look at a somewhat more complicated complet plot.
Just a note, what this says is that if r is less than 1, 0 is a global attractor. No matter where you start, the iterates are always going to wind up at 0. So if your population has r less than 1, you're doomed from the get-go.
Right. So basically the carrying capacity isn't high enough to carry that population. So we can do this for other points as well. So if we start here, we see that we're going to end up converging to this again, right? So if we start anywhere, we're going to end up converging. So let's take a bit more interesting function. So let me fill in the gaps there. So let's say we have r between 1 and 3. So that means, say, r equals 2. So that means it's going to go over the line y equals x. So then we have two fixed points within this region. But now we want to see what the stability is of these fixed points. So let's start somewhere. So we know from here that r between 1 and 3 is going to be stable, and r is going to be greater than 1 here, so it's unstable. But let's say we start over here. So then, as we did before, we're going to go to the left, and then we're going to go up to get our next point. So for the complet plot, we go left and right to get to the line y equals x, and then we're going to go up and down, up or down, to get to our f of x. So here we see that y equals x is to the left, so we go left. When we intersect it, we're going to go up to get to f of x. So that's how you draw these sort of things. So now, where are we going to go from this point?
Right.
So we're going to go to the right. We're going to go to the right to meet up with this, but now we have to go up. So that's our next point. So here it gets a little crowded, but we're basically going to go to the right again and up again, and we see that we're going to be converging to this fixed point. So that's for something to the right of this line, y equals x. Let's say we take something closer to x equals 0. So let's say we're here. So if we're there, we're going to go to the right to intersect y equals x, and then we're going to go up. So that's our second point. And we're going to keep on doing this. So we see again that we are converging to this fixed point. So no matter where we start here, we're going to get away from this fixed point and we're going to converge to that fixed point. So that's a bit more interesting. Now we have two fixed points we have things that are kind of moving around. But now let's look at the most interesting case. And then I'll tell you what your homework is on this.
So in that case, it says that you have a steady state for the population, right? It's going to converge to a half. No matter if you start at a non-zero value, non-1 value, the thing is going to converge to the midpoint of the sort of upside down parabola, and that's going to be your steady state population. So over time, your population, normalized population, is going to be equal to a half.
So now let's say that our R is greater than 3. So let's say it looks something like this. So again, we have the 2 fixed points. But now we're going to get this. So we know that it's both the fixed points are going to be unstable. But we want to see in what way it is unstable. So let's start off here, let's say. And then if we go to the left, we meet up here. And then we're going to go up, and we're going to get that point. And then we're going to go to the right, go down, and we get that point. And we're going to go to the left again, go up, we get that point. So now it's getting a little tricky, but this is going to be higher than this, so go a bit higher. So we get that point. So we're going to go down to get that. And we're going to go here. We're going to get that. But now this is lower, so we're going to go here. And we're going to get that point. And we go here. We get that. We go here. We get this point. We go here. We get this point. We go here. So let's see. It's going to be something like this. I don't know if I drew this correctly, but let's see what happens. And we're here. So it's converging. I don't know why. It's not supposed to be converging. So I clearly didn't draw it correctly, right?
No, you did.
But
It's converging to not a fixed point, but
it's going to converge. Yeah,
to a
it's converging to a cycle.
A 2-cycle.
Except here, it doesn't seem like it is
Well,
with my sketch.
you're drawing it by
so
hand.
I didn't draw it perfectly accurately sketch-wise, but it's going to do something like this. Let's take another point and see what happens.
And by the way, now the picture looks more like a cobweb. The ones before look like staircase maps. But now when you have something like this, it's sort of cobweb looking. That's why they call them cobweb maps.
So let's take some other point here, and hopefully I can draw it better by hand. Okay. So now let's start off over here. So then we're going to go to the right, and then we're going to go up, then we're going to go to the right, and we're going to go down, and we're going to left, and up, right, and then down, left, and then up, right, and then down. So we can kind of see what's going on with this. It's not really going towards any point, it's kind of wandering around. So it's going to be wandering around like this. And the dynamics are a lot more interesting. So now it gets kind of tricky to draw this. We draw a few more. So yeah, after that it's going to get really, really difficult to draw it. So it's kind of wandering around. So it's going to go into either a periodic orbit, or it's going to be chaotic. And we're going to see these cases on the homework. So let me see what I want you to do for the homework. So I actually, just to make sure that everyone does it properly, I kind of drew this on engineering paper. So I have everything outlined in the engineering paper, and basically what I want you to do is, for the boxes in black, so for the grids in black, just use the R values that's there and do the cobweb plot for, say, 5 iterations. So that's for the boxes on top in black, the little ones. And then for the bigger ones, I gave you an R value there. So you're going to kind of sketch this and then draw the cobweb plot for, say, 20 iterations or until you run out of room. So whichever comes first, basically. So you run out of room before 20 iterations, then just keep it as that. And then if you don't, then go on to 20 iterations. So I basically want you to kind of do this. So where I set the R value, that's where the top of the parabola is going to be. So you have a grid, so you can kind of match up the top perfectly. Of course, I don't expect a perfect sketch, but it should be quite good since I gave you a grid to work on. And do this in pencil. Don't do it in pen, because it's going to get messy in pen. Okay, so I want you to do that. Also, plot the time series for those R values. So where you have, so for each of the little grids, plot the time series for those. So basically what time series is you're going to take this xn and you're going to plot that versus n. So n is going to be your x-axis, and xn is going to be your y-axis. So just kind of plot that and see what you get for that. So that gives us a lot of information as well. And that should be very easy to do on MATLAB. All you're going to need to do is run a loop and use that map inside the loop. And then just do the plots. So if you aren't too experienced with MATLAB, though, you can kind of ask me for help with that. Okay, so that's homework for that. So now I want to talk about more complex things. So in continuous systems, so just like in continuous systems, discrete systems are going to have bifurcations, and we're also going to have periodic orbits. So I won't talk too much about bifurcations, but you can find more on that on page 358. So we're going to get bifurcations at r equals 1 and r equals 3. So these fixed points are going to be changing stability at those parameter values. So that's why we get bifurcations there. But you can read up on that on 358. But let me tell you some things about periodic orbits. So let's keep this.
Let me add a point here, because I think it's kind of interesting. This is sort of a difference equation version of the logistic equation from differential equations. If you write the x dt is equal to rx times 1 minus x, the solutions are fairly easy to find. You know, you do sort of partial fractions. You can write out the solutions. You know how they behave. They're very predictable. They're not unpredictable, anything like chaotic. So in the one-dimensional case, if you have a differential equation, dx dt is equal to f of x, you can never have chaos. You don't have enough room for the continuous case. This is a one-dimensional difference equation. As r approaches 4, the dynamics become chaotic. So discrete equations, discrete dynamics can show chaos at much lower dimensions than continued dynamics. As a matter of fact, if you have a differential, a system of two differential equations, planar differential equations, you cannot have chaotic solutions in 2 dimensions, not enough room. But for a difference equation, 1 dimension will do it. You can get chaos in 1 dimension. So it's one of the amazing differences between the continuous dynamics and the discrete dynamics is that discrete dynamics can get crazier, more chaotic at lot lower dimension.
Right. So actually, not next week. Last week we discussed the impossibility of periodic solutions in 1D, and obviously impossibility of chaos in 1D and
Well, it could be
and
a
2D as well.
circle could be period.
Oh yeah, of course, yes. Okay, so yeah, we talked about that as well. But yeah, we went over Poincare Bendix and stuff like that. Okay, so now let's talk about periodic orbits. So what does it mean for us to have a periodic orbit in a discrete system? So let's think of periodic orbits in continuous systems. So what do we get when we have a periodic orbit in continuous systems?
Centers.
Well, okay, so it basically kind of comes back to the same point, right? Now, in discrete systems, we can have, so a fixed point is going to be where it doesn't move, but now let's say we have 2 points where it just moves back and forth between them. So that's periodic, right? We can have 3 points like that. So it just kind of bounces around those 3 points. We can have 4, we can have many more points like that, where it just kind of bounces around those points. So now we want to figure out how we find these periodic orbits. Let me just define it, though. So I'm going to write it like this. And Professor Blackmore can correct the definition if something's missing. So I kind of came up with this definition. So we say a point, let's call it x hat, is contained in a, so we're going to call these periodic orbits cycles. So we're going to call it a k cycle. So that means k can be 2, 3, 4, etc. So a 2 cycle is where we have 2 points that bounce back. So it bounces back and forth between 2 points. And then if k equals 3, then it's 3 points. If k equals 4, it's 4 points. So that's what k is. So we say that x hat is contained in a k cycle if x hat equals fk of x hat, but, or and, x hat does not equal fk minus 1 of x hat, where fk is the kth iteration of the difference equation, or the map, xn plus 1 equals f of xn. So that's how we're going to define periodic orbits, or a k cycle. So basically what we want is, we want to, so let's think of 2 cycles. So if we want a 2 cycle, then we want all the things where the point is within this 2 cycle, so it basically bounces back and forth amongst each other, but now that also happens with a fixed point, right? So if we have a fixed point, we have 1 point where it just kind of stays there, but we can kind of think about it as it bouncing like back to itself. So we don't want to call a fixed point a 2 cycle. So that's why we have that x hat cannot be in this k minus 1 cycle. So anything in a lower cycle will always satisfy this equation, but we want to kind of discard those possibilities. So if we're thinking about a 2 cycle, we want to only consider a 2 cycle, not a fixed point. If we're thinking about a 3 cycle, a 2 cycle will also satisfy that equation, but we want to throw out a 2 cycle. We want to throw out a fixed point. So that's why we define it like this.
You have to be a little careful.
Mm-hmm.
For example, if you use that definition, let's say for a true 4 cycle, this could be comprised of two cycles.
That's
so
true,
what
yeah.
you need to have here is that
let's
it's
put a
a
caveat.
true k cycle if it's a fixed point for fk, but it's not a fixed point for anything smaller than k.
Right. So that's kind of what I say over
Well,
here.
you're thinking iteratively, but for example, if you had something that f4 of x hat is equal to x hat, possibly f3 of x hat is not equal to x hat, but maybe f2 of x hat.
Okay. So I have to put in
It's
all the
divisibility. I mean, that's fine if k is a prime, but if k is a non-prime, you have to make sure it's not a fixed point for anything strictly less than
Okay.
k.
So let's
It's called
put
the least period of the cycle.
x hat is not in f of x hat. So that considers the will consider every single case.
Or you
Okay.
could say it's x hat is not equal to fp of x hat for any p less than k.
Right. Yeah. That works too. Right.
Same thing.
Yeah. So now the definition is fine. So that's how we want to define a k cycle. That's how we want to define periodic orbits. So now let's look at the logistic map, and let's try to figure out what the 2 cycle will be for this logistic map. So how are we going to do that? What is f2 of x going to be then?
X hat is equal to F to
Just an
the
algebra.
So here, fx is going to be rx times 1 minus x. So then f2 of x, so yeah, what do we do for that?
we plug in that whole value for
Mhm.
x.
Okay.
In the same function.
So this is defined as f of x. So now we're going to plug this into here. But now I already did that. So I'll give you the homework for this. Now don't do the algebra by hand, just use Wolfram Alpha or Mathematica or something. So there's no point in doing all the algebra by hand, especially because I want you to find a 3 cycle. So that's going to be really tricky, but now Wolfram can do that quite easily. So use Wolfram Alpha or Mathematica. So I have it written down here. So r squared x times 1 minus x times 1 minus rx times 1 minus x. So that's what we get for f2 of x. So it would be quite tedious to get that by hand. You plug it into Mathematica and you get it right away. So we're going to get that.
by hand.
Huh?
You could do that by hand.
You can, yeah. But it is
Recorded.
tedious. But now if you're going to do a 3 cycle, you take this, plug it in. Nah, forget it.
Yeah.
We have computers that can do that. Okay, so we get this, and now we're going to do what? So what equation do we want to solve?
So all that is equal to x star.
Okay.
X is-
So, or x hat, let's say. So let's write it like this. R squared x hat times 1 minus x hat times 1 minus rx hat times 1 minus x hat minus x hat equals 0. right? So those are the same things, right? But now, what do we want to do? So that's a quartic equation, right? Do we know the formula for a quartic equation? So well, yeah, humans, yeah, as humans, I guess in the collective knowledge, we know what it is, but it's like a page and a half or something. So we don't need the quartic the formula for a quartic equation though, right? So what can we do with this? How do we remove the fixed points from this? So the fixed points are going to satisfy this as well, right? How are we going to remove those fixed points? How are we going to discard those fixed points from that equation? So let's do one fixed point. X star equals 0, right? So if we have x star equals 0, well, look at this. We have x hat here and x hat here. So now we got rid of x star equals 0. So to get rid of x star equals r minus 1 over r, we have to factor out x star minus r minus 1 over r, right? So it's basically all the factors, right? So we have to factor that out. When we factor it out, so let me write it down, factor out x star minus r minus 1 over r. So now this by hand would be pretty tedious. So if you do this on Wolfram Alpha or Mathematica, it gets a lot easier. So you can do this on Mathematica, and if you do this, you get this. So if you factor it out and then solve for x hat, so if you factor this out, then you're down to a quadratic equation. And you can solve a quadratic equation very easily. So obviously you can do that on Mathematica as well. So then we're going to get that x hat is going to equal 1 over 2r times r plus minus, or r plus 1, sorry. R plus 1 plus minus the square root of r minus 3 times r plus 1. So we get that. So those are the 2 points that are contained in this 2 cycle. So it's going to be bouncing between these 2 points. But what do we notice about this? Do we notice anything about what happens if we change r?
You get an imaginary number again?
Okay, so what happens with imaginary numbers though?
Is it going to change the cycle of it?
So do we want x to be imaginary? So we don't want x to be imaginary because it's a map from the real line to the real line, right? More precisely, it's a map from 0, 1 to 0, 1. So we don't want it to be imaginary. So if r is such that it makes it imaginary, then we can't have it. So r can't be less than 3. So we only get 2 cycles if r is greater than 3. So that's what this says. Right? So we kind of saw that in our cobwebs. We're only going to get periodic orbits if we have r is greater than 3. So at r equals 3, we're going to get what is called a bifurcation. And that's more specifically called a period doubling bifurcation. So what happens there is that we're going to have this fixed point, but now it's going to bifurcate into a 2 cycle. And that's going to bifurcate, and then that's going to bifurcate. So we get 4 cycles, and then 8 cycles, and etc. until we reach chaos. So there's more on that on page 353 if you want to read more on period doubling. So he has some very nice diagrams of that. And you'll see so you won't see this, but you'll see like things that are similar to the time series he has, Strogatz has in the book when you do your time series plots. So you'll get the same sort of things that he gets for these things. So let me tell you the homework for that. So I basically want you to just find the form of the 3-cycle. So use Wolfram Alpha for that. So all you're going to do is find F3. So you're going to take this, plug it in here, find F3, discard all the 2 cycles and fixed points, and then you'll get an equation for the 3-cycle. So find that, and don't do the algebra by hand. Also, plot F3 as well. So when you plot F2 and F3, you get kind of a better intuition about these things. So if you plot F2, you'll see that the fixed point and the 2 points that are part of the 2-cycle are going to intersect the line y equals x. So I want you to do that for F3. So plot F3 and y equals x, and then explain if you think a 3-cycle exists or not. So explain or when you think a 3-cycle exists and when you think it doesn't exist. So I'm not going to penalize for a wrong answer there. I just want to kind of get you to think about it. So just plot F3 and y equals x. And yeah, so plot that for, let's say, for the R value that you have for your cobweb plot. So for that same R value, plot F3. So that's that. And then let's talk a little bit about sensitive dependence and Lyapunov exponents. So a tool that we can use to see if something is really sensitively dependent is using something called Lyapunov exponents.
Just a word here. The existence of 3 cycles is crucial in this case, because if you have a 3 cycle, then you have chaos. And it has to do with this, some theorems by a Ukrainian mathematician who introduced some kind of an ordering that says whenever you have a 3 cycle, then you'll automatically have periodic cycles of all periods, Maybe you want to check that out on the 3 cycles.
Right.
Period 3 implies chaos, a paper by York, but done earlier actually by a Ukrainian fellow.
So I think Strogatz goes a bit deeper into like period doubling and things like that. So it's a good idea to read up on Strogatz as well. Okay, so we want to quantify sensitive dependence. So we're going to use something called a Lyapunov exponent. So Lyapunov's name is spelled differently everywhere. So in Strogatz it's spelled like this. So Lyapunov exponents. So basically consider delta naught as the separation. So let's consider delta naught as the initial separation between 2 points. Then we know that delta n, so the separation after some time, is going to look like this. So Strogatz kind of derives everything. I'm not going to do that here. But say after time n, we get that delta n equals delta naught times e to the n lambda. And then, so this is the Lyapunov exponent. So this is what we call a Lyapunov exponent. and we can find what lambda is explicitly. So Strogatz does the derivation, but I'll just tell you what it is. So lambda equals lim sup. So let me write this better. Lim sup as n goes to infinity. So in Strogatz, it's just written as a limit, but it really should be written as lim sup. So the limit supremum. But we can kind of think about it as the limit if you haven't taken analysis. So the lim sup of 1 over n times the sum from I equals 0 to n minus 1 ln f prime of xi. And the derivation of this is on page 366. So we should know what this is. So I have this in the PDF notes as well. So now let's just figure out what this formula is going to be for the logistic map. So what are we going to do then? So we need to calculate f prime. Do we have what f prime is in the notes? So what do we get for f prime? It was like r minus 2rx, right?
Yeah.
Okay. R minus 2r xi. So then our lambda for that case is going to be lim sup of as n goes to infinity of 1 over n, the sum from I equals 0 to n minus 1 of ln times, or ln of r minus 2r xi. So we're going to get that, right? So that's basically what the Lyapunov exponent is going to be. So obviously it can be quite difficult to compute by hand, except for a few very nice systems. So you can't really compute this by hand for the logistic map, but you can approximate it. So that's kind of what I want you guys, what I want you guys to do for the homework for this. So approximate the Lyapunov exponent of the logistic map. So basically this for the R that you use in your cobweb. So the R that you use in the red one.
Okay.
The red R. So so I don't want you using those other R's except for the cobweb itself, but the red R are the ones that I want you to use for everything else. So I'll type this up in an email and send it to you guys. But that's going to be the interesting one. The R's that are in red. So I want you guys to approximate this. So you can do that on MATLAB. So I want you to do it numerically. And so let's talk about how we can approximate it. So how do we think we're going to approximate that?
Chunk theory?
That probably wouldn't help us too much here. So we're just going to keep iterating it, and we're going to get up to a high enough iteration, let's say. So first of all, we want the transients to die away, right? So we want, so maybe it wouldn't work for the R that we have, the R values that we have on the cobweb. Let me think about it. But if we get the transients to die away, then it's a lot easier to calculate or to approximate the Lyapunov exponents. So then we can kind of bound what it is and then compute it from there. But now if we have a chaotic system, then we're not going to get those transients to die away. So then we have to think about it. But you can, so if you have a system that's converging to a fixed point, then you can calculate it just by taking a big enough n, and you'll get a decent approximation for it. But the interesting one is when you have a system where you have R such that it's chaotic. But that's a lot more difficult to compute. So I'll email you guys the homework for this, and then we'll see what we can do. So any?
Yeah. So I mean, this lambda is an indication of what's known as sensitive dependence on initial conditions. So if lambda is positive, if this Lyapunov exponent is positive, then this is going to exponentially expand as you iterate it. Makes it very hard to predict. This sensitive dependence is very closely related to some mathematical and intuitive notions of what chaos is. The old thing about if a butterfly flaps its wings in the Brazilian rainforest and there's a non-linear chaotic system, that little flapping of the wings could cause a hurricane in the northern hemisphere, that kind of a thing. On the other hand, if lambda is negative, well, very, very nice behavior. So lambda being positive is kind of an indicator of chaos. Right. There are, by the way, there are some nice little programs for computing Lyapunov exponents. I think you can get a few actually on the web. They're freely available.
So they deal with higher dimensional systems because that's when it gets really difficult.
Yeah, usually, but they can be kind of jerry-rigged to do one-dimensional cases as well. And as Amit said, only in very few cases can you actually compute this Lyapunov exponent directly. A nice one, which is kind of a piecewise linear version of the logistic map, is the tent map. So you take that thing and you straighten the two sides. You can actually then write out what the iterates are going to look like exactly and find out exactly what the derivatives will be at those various points. Well, the derivatives are going to be plus or minus constants. So you can actually find out, you can actually compute directly what this limit is. The limit exists, and it's positive if these slopes are big enough for the tent map. If you have a very squat tent, it's not going to do much. For example, if it's a squat tent, then again you can have the origin as a global attractor. But if it's steep enough, you're going to get chaotic motion, and you can analyze things like the Lyapunov exponents directly, and a lot of other things. You can determine all the periodic orbits and all of the iterates. It becomes very easy in only certain cases, but very few.
So I should write that down.
Take a look at the tent map.
Lambda greater than 0, indicative of chaos. And what should we call lambda less than 0? Well behaved?
Regularity.
Okay.
Non-chaos.
So yeah, those are maps, and we'll deal with some of that, but we'll mostly deal with continuous dynamical systems, because that's what most of the very early physical systems were. So like Lorenz's equations, and for the double pendulum and Chua's circuit. So those are all continuous. So we'll mostly be dealing with continuous stuff, but it is very important to know about maps, and it's a very simple way to get to chaos at times. So unless you want to add.
Well, there's a nice relationship between maps and continuous dynamical systems in terms of what are called Poincare sections. So very often when you have a continuous dynamical system that has some sort of recurrence that keeps coming back more or less to where it started, by looking at the intersections of those trajectories with a lower dimensional, let's say, hypersurface, you can tell a lot about what goes on. I'll just sort of draw a picture in the air. suppose you're in three-dimensional space and you have a continuous dynamical system and you're looking for periodic orbits of that thing and you want to try to reduce the dimension. If you know that the periodic orbits, not periodic yet, but if you know that the orbits are recurrent, that is, they tend to come back pretty much where they started, you can find a small two-dimensional plane called a transversal and look at the intersections of that continuous orbit as it goes around. Okay, so how do you find a periodic orbit of the continuous map? You find a fixed point of the intersection map. So in other words, if the thing comes around and its next iterate, it hits at the same place it started, that says that the trajectory is closed. So there's a nice relationship, a useful relationship between discrete dynamical systems and continuous dynamical systems through these kinds of constructions.
So we'll actually talk about point array maps next week. So we'll go over all that stuff. So if there are no questions, then I guess that's it for today.
I have a question.
Yeah.
What
Mm-hmm.
what is the xi in this
Oh, okay, so those are iterates basically,
okay.
right? So you start off, so it's going to start off with I equals 0. So you start off with an initial point,
Okay.
and then you're going to iterate that point, but you're looking at f prime of xi. So
Okay.
xi are just like the xn's basically.
Okay.
So you're looking at that. So you're just iterating it. So in order to find your xi's, you have to iterate it, right? So xi plus 1 is going to equal f of xi. So in order to find your xi's, you have to iterate the map.
Okay.
So you can do that on MATLAB fairly easily. So when you do the time series, you can kind of use that code, and then you can use that code to code this in as well. So when you do your time series, you're going to find the iterates. So you can do it kind of simultaneously.